Welcome to the outside of my house. Here's my air conditioner unit, or rather the external part of it. And inside of here is a fan that basically blows air past a series of flat plates. So if you look inside there, I'll try to get the autofocus on there. You can see basically a radiator, or essentially a bunch of flat plates in the wall. So basically what goes on, there's heat inside my house. There's a compressor that basically does fancy thermodynamics, and eventually the fluid from the compressor basically comes out as a very hot thing, expands in here, and that heat gets transported via fins. So this fan basically blows air through those fins, and in a way to basically reject heat that was at one point inside the house outside of the house. So these engineers basically needed to know, hey, what is this heat transfer process when we have a fluid flowing past a flat plate? So not just in air conditioner units like that, but all the time, engineers have flow past flat plates where the plate is hot or the plate is cold, and the fluid is hot or the fluid is cold, and there's heat exchanged between them. So today, we're going to talk a little bit about boundary layers. And in particular, how boundary layers pertain to flow past flat plates, and how that could eventually impact heat transfer. So boundary layers and its connection to flow and heat transfer past flat plates. And whether these are flat plates as part of an air conditioner unit or flat plates as part of a heating system for a bioreactor, or a coolant system for a medical device, or a medical imaging device, something like that, we encounter flow past flat plates all the time in bioengineering. So when we're talking about boundary layers, these boundary layers aren't necessarily relevant just for heat transfer, but there's also sort of hydrodynamic concerns as well. So we'll talk about two boundary layers: the velocity boundary layer, which is basically a description of how does flow far away from the plate affect flow very close to the plate. What is the relationship between the molecules very, very close to a flat plate versus far away from it? How does velocity transition between the plate and what's flowing around it? And then there's what's called the thermal boundary layer, which is basically how does temperature transition, for example, between the hot surface of a plate and cold fluid far away from it. In our discussion of these two, we'll want to, these will sort of set a qualitative framework for what we'll be talking about in terms of heat transfer. And then we'll sort of move on talking about surface temperature. So for example, surface temperature of a plate, surface heat flux, if you remember, heat flux is watts per square meter. So what is a relationship between surface temperature, surface heat flux, and convection coefficient? Or you might call it H. What is the relationship between these three things for these flat plates? We have already related them in some ways to Newton's law of cooling. So we might encounter, certain situations where, what's constant, what's varying, across the surface. And we'll look at two specific cases later on. We'll look at one case where we have a constant surface temperature and the surface heat flux and H are varying. And then we'll look at a case where we have a constant surface heat flux and surface temperature and convection coefficient are varying. So basically this is always going to vary, and then if you have one constant, the other one is going to have to vary. But we'll talk about that in a little bit more detail later. Then we're going to say, hey, there's this convection coefficient, but in a way that kind of ties back to what we were talking about with pipes. When we were talking about with pipes, we said, hey, we're just going to deal with an H that's kind of averaged over the whole thing. And, there could hypothetically be entrance lengths that are important. Well, it turns out that for a flat plate, there's not really a well-defined entrance length at all. Basically, the whole plate kind of has this developing boundary layer. So there's not really a fully developed plate. Basically, the flow is always developing across a plate. So with that in mind, entrance length is essentially always important. There's not really a well-defined entrance length at all. The whole plate is the entrance length. So for flow past plates, we'll need to always deal with what we'll call a local heat transfer coefficient, or a local convection coefficient, versus what we'll call a spatially averaged convection coefficient. And what the variable that we use for a local convection coefficient is going to be h sub x, and the average convection coefficient across the whole plate is what we'll call h sub l, with a bar over the top of it that's basically indicating the average. So these are the two convection coefficients that will be important, and we'll sort of talk about basically why, under what circumstances, for what types of problems might we use h sub x, for what types of problems might we use h sub l, what are the relationships between them, and what relationships do these allow us to make between other things like heat fluxes and temperatures and heat flows and things like that. Then we'll wrap up today's discussion with we've talked about, hey, there are these H's and H bars. How do we go about finding H's and H bars? We'll talk about a few new Nusselt numbers. And remember, these Nusselt numbers are basically the sort of normalized or non-dimensionalized H's. If we have an H sub x and an H sub l, then we're basically going to need two different Nusselt number formulations, one that corresponds to an H sub x and one that corresponds to an H sub l. So we'll have two new Nusselt numbers, one that I'll call Nu sub x, that basically corresponds to H sub x, and then another one that's basically Nu sub l with a bar over the whole thing that corresponds to H sub l. So in the way that there are two heat transfer coefficients, one that sort of locally relates a local temperature to a local heat flux versus an average temperature to an average heat flux, there's going to be separate Nusselt number formulations for each of these and separate equations that we'll talk about in an upcoming lecture. So this is what we're going to talk about today. So let's start by talking about this velocity boundary layer. So imagine a flat plate. Could be this sheet of paper, could be like the very edge of the table that I'm working on right here, or could be one of those fins in the radiator that I was showing you earlier for my air conditioner. So if I think about a flat plate, I might think about a solid surface like this. And here we're basically going to imagine a scenario where I have fluid kind of flowing tangentially past that surface. So let's say I have some fluid coming in, there's a leading edge of this plate right here. I have fluid coming in, and before the fluid really encounters the plate, that flow is, give or take a little bit, going to be roughly uniform. Right? So right here, we might have this sort of uniform flow. And we might say this uniform flow has some velocity, v infinity. We might give ourselves a coordinate system. I'll call x my coordinate sort of down the plate, starting at the leading edge. And I'll call y my coordinate sort of that starts at the plate and kind of moves upward from this. Well, this fluid, or this fluid velocity profile, starts uniformly, But what happens to these molecules as soon as they start encountering the plate? Well, the plate's not moving, the velocity is, the flow is moving, and we can't sort of have that, that discrepancy here. So so basically what happens to the fluid? Well, the molecules of fluid immediately adjacent to the plate basically don't move, but the molecules, pretty far away from the plate are basically going to go along at their original unperturbed velocity like this, and there's some kind of transition between the molecules that aren't moving and the molecules that are moving. And what it turns out that happens is, during right at the leading edge of the plate, this transition happens over an almost infinitesimally small distance. But as we go down the plate, the thickness of this transition region basically grows. And it turns out that it basically grows without bound. So basically, it doesn't just sort of like level off after a certain distance. It just keeps growing and growing and growing, and it basically grows proportionately to the square root of x. So, I didn't draw it perfectly right here, but if you were to sort of trace out the thickness of this transition region, basically as x gets bigger, this boundary layer thickness becomes bigger. And basically what we call here, this transition region between no velocity right at the plate and the sort of unperturbed free stream velocity, we call this the boundary layer. So we call this boundary layer, and it's basically its thickness is proportional. It's proportional to square root of x, and some other factors that affect it are basically the velocity. It turns out the magnitude of the velocity affects the thickness of the boundary layer, as does the fluid density, viscosity, and of course x position as well. So the boundary layer basically is a function of these variables right here. The thickness of the boundary layer is a function of that. So up right at the leading edge, we have this uniform velocity comes in, and basically the transition region between where we have no velocity at the plate and the free stream velocity kind of gets thicker and thicker as we go along. So, here this transition happens quickly, here it happens slowly. Why do we care about this? Well, you can imagine if I have cold fluid coming in, the growth of this boundary layer, I essentially have more velocity coming in, more fluid coming in here than going out here, so the growth of this boundary layer actually steers some fluid out of the boundary layer. And the fluid that gets steered out of the boundary layer carries heat. Carries heat with it. So we don't just care about this from a sort of hydrodynamics perspective. I mean, we do care about it from a hydrodynamics perspective, right? There's, this boundary layer affects things like shear stress. If we were designing airplane wings, we would care a lot about this boundary layer, but we might care about it a lot from a heat transfer perspective, right? Because basically, if I have fluid coming in and then this the fluid slows down as it encounters the plate, well, due to conservation of mass, some of that fluid has to get pushed out of the top of the boundary layer. And if you have cold fluid coming in and getting pushed out of the top, that carries heat with it. So this process here, this conservation of mass, essentially is what governs a fair fraction of this heat transfer. So that informs, this idea of this hydrodynamic boundary layer and fluid that encounters it and gets steered up informs the idea of the thermal this idea of the thermal boundary layer. So what does the thermal boundary layer look like? Well, you can imagine I might have a plate. Let's for now basically say we have a hot plate and cold fluid. So we have a hot plate and cold fluid. And let's basically say, I have the same coordinate system, x and y. And let's imagine, here, let's say far away from the fluid, or far away from the surface of the plate, I might have some temperature, let's call it T infinity, right, of the fluid far away from the plate. Well, you can imagine as the fluid is coming in, basically all of the fluid kind of has has a temperature T infinity coming in. But let's say I have some plate with some surface temperature right here that's, let's say, hotter than T infinity. So as soon as this fluid encounters the plate, the molecules of fluid immediately adjacent to that surface, basically those molecules get, almost instantaneously become at a surface temperature Ts. Whereas fluid that's farther away from the plate might remain unaffected for a while. So it turns out that there's this thermal boundary layer that develops, and this thermal boundary layer might look something like this. Outside of the thermal boundary layer, my temperature is basically at T infinity, but if my Ts is, let's say, hotter than my T infinity, I'm going to transition from my hot Ts down towards T infinity over the thickness of this boundary layer. So here I'm kind of plotting, the length of these lines is proportional to the temperature. So you can basically imagine the temperature being very hot close to the plate and kind of gradually approaching T infinity as we sort of exit the boundary layer. So I'm still T infinity outside of the boundary layer. I'm Ts at the surface inside the boundary layer. And you can imagine there's this thickness here. There's this thickness of this boundary layer here. It turns out this boundary layer also grows without bound, proportional to square root of x. And I should clarify that it's proportional to square root of x for laminar flow only in these cases. You can't have turbulent boundary layers. We'll talk about that later in this lecture. But basically, these, like the thermal boundary layer, basically grows without bound as well. So what's going on here? Well, this boundary layer sort of grows here, and it basically increases the distance over which the transition happens from Ts to T infinity. So right here, there's a greater distance there's a greater distance of the transition from Ts to T infinity, for example, compared to right here. So how might this affect heat transfer? Well, first, let's just say let's clarify a couple of things here. We might this thickness of the boundary layer, oftentimes people call it delta sub T, and it's a function of x. This thickness of the hydrodynamic boundary layer, people often just call it delta, and it's a function of x. So that's just some terminology here. This thickness of the thermal boundary layer is governed. This is a function. This is a function of the same things that the hydrodynamic boundary layer is a function of, but it's also a function of the thermal properties of the fluid as well. So it's a function of K fluid and the specific heat of the fluid as well. So that's basically what this thermal boundary layer tends to depend on. So take a moment now. Let's look at this case. Let's say for this case down here we have a constant surface temperature. Let's look at two regions of the flow, or two regions of the plate. I'll call it region 1 right here at the upstream part of the plate. Let's call it region 2 here at the downstream part of the plate. So take a moment now, pause and ponder. Which region has the higher which region has the higher heat flux coming out of it? Does region 1 have the higher heat flux coming out of it? Region 2, or are either the same as each other? Or do we not necessarily have enough information to know? So take a moment now, pause and ponder, which region do you think has more heat flowing out of it? All right, so hopefully we've had a minute to pause and ponder. We can almost think of this a little bit, give or take a little bit, almost like a conduction problem, right? So in a sense, heat kind of needs to get conducted by the fluid as it leaves. Yes, there's some of this heat carrying with it phenomenon, but in general, we like to think of heat flows being sort of proportional to a temperature gradient, or heat flux being proportional to a temperature gradient. So heat flux, we might like to think of this as proportional to a couple of factors, but mostly proportional to dt dy in this case, right? Since temperature is varying with y. So I might say this dt dy is in a way at least proportional to Ts minus T infinity divided by the thermal boundary layer thickness, right? So basically, whatever temperature gradient we get right at the surface is in a way sort of proportional to the temperature difference, Ts minus T infinity, and also this thickness, right? So basically, as the thickness of the boundary layer grows, this temperature gradient originally starts pretty steep, right? It originally starts pretty steep, but then it shallows out as that temperature transition happens over a greater and greater distance. So we can think of this as like Ts minus T infinity over delta sub T. It's not an exact equation, but it's at least proportional to this difference. So if we think about it as the boundary layer grows, heat flux lowers for a constant surface temperature plate. So what does that mean? That basically means this downstream region 2, basically is not transferring fluid, or not transferring heat to the fluid as effectively as the upstream one, right? So this has better or more rapid heat transfer, and this has poorer heat transfer. So, one rationale is basically, the thickness of this boundary layer is an explanation. We can also think about it, this region at this upstream region of the plate gets basically fresh fluid, right? This gets fresh, cold fluid flowing right next to it. But this downstream region of the plate doesn't get that fresh fluid. It gets all of the upstream junk, the slightly warmed up fluid that was flowing over it. So basically the downstream region of the plate gets all the polluted junk, from the upstream region, whereas the upstream region gets gets fresh fluid going in, fresh cold fluid. Delicious, right? So the upstream region of the plate oftentimes gets better heat transfer than the downstream region of the plate. So as you increase the length of the plate, yes, you still get overall more heat transfer to the environment, but it's kind of a decreasing marginal return. So when you're designing heat exchangers like those fins for the air conditioner that you saw earlier, oftentimes what people would rather do is, rather than just have one big long fin, they'll have a series of parallel shorter plates, because then each plate will be getting the best flow. So it's better to have two short plates than one long plate in terms of heat transfer. But there might be trade-offs in other aspects of your engineering design. So this is the nature of the velocity boundary layer and the thermal boundary layer, qualitatively anyway. So now let's talk a little bit about surface temperature, surface heat flux, and the convection coefficient. So let's put some equations to the relationships between surface temperature, surface heat flux, and convection coefficient. And in particular, we'll look at cases where one of these is constant and the other two vary, or this one is constant and the other two vary. So imagine I have a plate. We could, and let's say x is the position. So I have flow coming in over the plate like this, and there's going to be heat transferred between the plate and the fluid. So in in lectures prior to today's, we said, hey, heat transfer between the plate and the fluid can be described with Newton's law of cooling, which basically stated, hey, the heat flow due to convection is proportional to a couple things: h times the surface area times Ts minus T infinity. And this has worked great up until this point right here. But what this relationship does is it essentially puts the whole plate in aggregate. It's not necessarily allowing for variations in temperature across the plate or variations in heat flux. Is part of this plate rejecting heat better than other parts? Well, for darn sure we know there is, right? We know from this rationale that part of the plate might be dumping heat more than the other part of the plate. Or in some other cases, maybe we have a case where we don't have a constant surface temperature of the plate, but maybe part of the plate is hotter than other parts of the plate. So we might ask ourselves, hey, this can't describe temperature varying over the plate, or how heat flux could be non-uniform. Right, so this sort of says, hey, there's one singular Ts that applies over the whole plate, and this is basically saying, hey, there's one singular heat flow out of the whole plate. This is kind of just lumping everything in aggregate. But a lot of times, for design of heat exchangers that use these flat plates, we might need to account for some of these variations. So we need a little bit more of a sophisticated analysis. So oftentimes what we do is reformulate Newton's law of cooling on the per unit area basis. So rather than using a heat flow, which is going to have units of watts, we instead describe things with a heat flux that has units of watts per meter squared. So we'd use a heat flux that has units of watts per square meter. And it's essentially just dividing out by AS, right? So this heat flux is Q convection. We still have an H, and then it's Ts minus T infinity. And because this is on a per unit area basis, we're not lumping together the whole plate, but this is something that essentially could apply at this point here, or this point here, or this point here, or this point here. And for all of these points, they might have a different heat flux out of each of these points, or a different Ts out of each of these points. So basically all of these points might have different heat fluxes, different surface temperatures, and different H's, right? So all of these points here could have different each point could have different H, Ts, and or heat flux. And this Newton's law of cooling doesn't allow us to get to this subtlety, but this subtlety might be important for our engineering design. So what do we do here? This H and this H, we're allowing for the idea that H could vary over the surface. So we're going to need to be a little bit careful kind of from now on with our H's. So I'm going to give this h a subscript x, and I'm going to sort of distinguish between a couple of different h's here. So what this hx I'm using to describe is what I'll call the local h, which essentially is almost like a point-wise description. It's saying, hey, at this point, what is the relationship between the watts per square meter flowing out of the surface, this particular point's TS, and this particular point's H. So it's a local H, and each point on the plate has a different H sub x. And this positionally varying H sub x allows for this non-uniformity that we're trying to get at. So let's look at two cases that we might frequently encounter in bioengineering. Case 1, which is basically, hey, we're going to assume the surface temperature is a constant, and if the surface temperature is a constant, so if surface temperature is constant, then our H sub x and our heat flux, Q convection, both vary with x. And why? Because this equation here is basically this is universally true for each of these points. So what does it mean? Basically, if Ts and T infinity are constant, and we know from our qualitative description here that heat for a constant surface temperature plate, we're going to have more effective heat transfer out of the leading edge of the plate than the trailing edge. If that's the case, if our surface temperature is constant, we know that the heat transfer coefficient basically goes down as we move down the plate due to the sort of polluted air argument. So what does that mean? That means basically our Q dot convection also has to go down, right? So basically, if this is constant over the plate, then both of these kind of go down as we go downstream of the plate. Then our Q dot convection vary with x, and they typically, so H sub x and Q convection vary with x, and they typically decrease with x. Let's look at another case. Case number 2. So case number 2, so not always, it's not always true that we have a constant surface temperature fin, right? We'd only really have a constant surface temperature plate if we had, a whole bunch of heaters and a whole bunch of little temperature sensors that were kind of running little control loops to maintain this at a constant surface temperature. That's not always true. A lot of times we might have a case where, hey, we don't necessarily have a constant surface temperature, but we sort of have this, have a heater that's, or a bunch of heaters that are kind of embedded in this plate right here. So this might be, for example, if you had an electric space heater. If you had an electric space heater, they're basically running electricity through these flat plates, and these flat plates basically heat up, kind of sort of generating a uniform heat flux out of this whole case, right? So, case 1 is, let's say like we had temperature controller embedded in the plate. Case 2 might be like a space heater with uniform resistors, electrical resistors throughout. So if that's the case, then if you have a constant convective heat flux, basically the electrical resistors start heating up, and they sort of each resistor in each little cell or each little region of the plate, if each of these is generating a constant heat flux, But we know that poorer heat transfer occurs on the downstream region of the plate. So if our Q dot convection is constant, then, so if this is constant, and this gets worse as x goes on, right? So as x goes on, we get sort of more of this polluted air phenomenon. Then surface temperature must be rising as we move down the plate. So if our convective heat flux is constant, which might be the case if we have electric heaters, then Ts must rise with x, as we know h sub x falls with x due to the sort of polluted air phenomenon. And I'm saying air here because a lot of times we have air flowing past flat plates, but this also applies just as readily to systems with water as well. So in both cases, in both the constant surface temperature and the constant heat flux case, this equation basically always applies. So this equation is true for both of these cases. It's just which of these terms are constant, which of these terms are varying. This h sub x always varies. This one basically always varies. This basically always decreases with x. So it's basically like if this is constant, then this needs to decrease with x, or if this is constant, then this needs to increase with x, such that their product ends up being constant, depending on which case you're dealing with. All right, so this basically describes locally what's going on. Right? This h sub x says, hey, if I have some, any of these particular points, what's going on in the plate? I can relate that, like, what's going on at this point in the plate to what's going on, in the flow around it, Ts and T infinity. So I can basically relate heat flux at a point, H at a point, Ts and T infinity all at points. But, a lot of times I don't necessarily care about points. If I want to do well in the class, I care a lot about points. But I don't necessarily care about points on this plate, right? So a lot of times what I might care about this only so much as, can it build me something that works a little bit more towards the sort of easier to use or aggregate relationships that I talked about earlier. So this brings us towards caring about local versus average heat transfer coefficients. So local versus average H. So local H is what we talked about earlier. So first let's talk about local. The local relationship is basically saying, hey, at a point, locally, I might say my Q dot my convective heat flux is equal to H sub x times Ts minus T infinity. But a lot of times I don't really care about the details of what's happening at every point. I might say, hey, over the whole area of the plate, what is the averaged over the whole plate? What is my average convection? And if it's averaged over the whole plate, I'm going to put a bar over the top of it. I might say, hey, what is my average heat flux over the whole plate? And in that case, it's not going to be the same H, right? Because because we knew H was varying with our position down the plate, I might say, hey, over this whole plate, what's the average H over this whole plate? And the average H over this whole plate essentially is more similar to what I'm used to dealing with over here. Right, so this average heat flux is basically going to be equal to my averaged H, and I'm going to average it. It's not sort of going to be this function of x that I'm talking about earlier, but essentially an h that's averaged over the whole length, over the whole L, over let's say the whole L of the plate. Right? So if the plate has some overall length L, I might say, hey, over the whole plate, what is the averaged h over the whole distance, starting at the leading edge and going all the way to the end right here. So I might use an average h sub L to do this, and this would allow me to essentially relate average Ts minus T infinity. So, you know, I can kind of relate all of these averaged quantities to one another with an average H sub L. So I can relate essentially heat flux at a point to to convection coefficient at a point and surface temperature at a point, or over the whole plate, what is the averaged Q convection? And you know, this essentially is basically equal to my Q convection divided by the surface area, right? So, you know, the total heat flow in watts divided by the square meters that watts came out of is my average heat flux, which I can relate here. So this is actually similar to what we've been using, where I sort of assume, you know, the whole surface has some average temperature, or maybe even the whole surface is at some one particular temperature. And I'm just sort of saying, hey, on average, what is the whole heat transfer coefficient, neglecting the fact that it truly varies across the surface. So this is similar to what we've been using. You know, this is the useful one if we want to kind of relate sort of bulk. So this is the best to relate bulk heat flows. So this is best and what do I mean by bulk heat flows? I'm basically saying, you know, hey, like what's coming out of the whole plate? You know, basically a whole plate if you're doing some kind of whole plate analysis. This one is most useful if we want to say, hey, what is the worst or best possible point on the plate? So for example, is there some point on the plate that gets too hot? Or I guess I don't really mean best or worst, but I mean, you know, without sort of judgment on temperatures, what is the hottest or coldest point? For example, like, does every point on some hot plate remain below some safety threshold, or what is like the maximum heat flux, something like that. Something like that, right? So local investigates this local relationship allows us to say, hey, is there any particular point, you know, where's going to be the hottest or coldest point? You know, this analysis basically allows us to investigate single points where some single point being above some hot or cold threshold might be problematic. Whereas this one just says, hey, let's lump everything together. Let's try to get some overall wattage out of some plate in response to some kind of average temperature difference. So let's tie this back. Let's tie this these ideas of, you know, two different H's with different applications to relate different local or averaged phenomena. Let's tie these to two Nusselt numbers. So, so for pipe flow, back to our previous lecture, we only really cared to investigate the average phenomena, the average temperature, and the Nusselt number that we had for pipe flow was an average quantity. We only really developed or discussed an average pipe flow. And it was based on the diameter. So for pipe flow, it was H bar, the Nu bar indicated the average, D indicated that the length scale was diameter. So it was H times D over the thermal conductivity of the fluid. For a plate, there's not some sort of intrinsic length scale, right? So for the pipe, we said, hey, there's this length scale, the diameter, and this diameter is really basically governing, what is the temperature difference between, some point in the core of the fluid and, some point on the surface, right? This length scale really helps define the heat transfer. For plates, what is our length scale? Well, we can essentially choose two length scales. One would be the length scale L for the entire plate. Another length scale would be from the start to whatever point X we're at here. And it turns out that X is basically the appropriate length scale for the local thing, because we're basically saying, hey, what's going on right at this point here? Basically, what's downstream of that point doesn't really affect what's going on at that point at all. Whereas if we're thinking, hey, on average, what's happening for the entire plate, we kind of need to consider the whole length of the plate. So for plates, we basically have the Nusselt number sub X, which doesn't have a bar over it for the local. We define the Nusselt number this way, and for the average quantity, the Nusselt number sub L is the average H times L over K of the fluid. So there we have it. So what I have here is basically the definitions of the Nusselt numbers, and it turns out the problem-solving strategy for finding our own H, basically, how do we go about finding our own H? Well, we basically know what X point we're choosing to investigate. We know what the properties of the fluid are. So if we have some way to look up equations for Nusselt number based on various parameters of the flow, once we find a Nusselt number, then it's pretty straightforward to find an H. So in the same way that Nusselt number was essentially a normalized H for pipe flows, there are these Nusselt numbers which are essentially normalized H's for plate flows. We just need a different one for whether we're talking about, what is the local H happening right at this point here, or what is the H averaged over the whole length of the pipe. So those are our new Nusselt numbers. And in the same way that we had equations for these Nusselt numbers as functions of Reynolds numbers and other things, we can develop what these functions for Nusselt numbers are as functions of other stuff. So we might anticipate, so we can follow a similar rationale to what we did for Nusselt numbers for pipe flow, or the dependencies for H, right? So for local convection on a plate, well, what do we expect H to be a function of? So local, I'm talking about H sub X. So we anticipate H sub X to basically be a function of a whole bunch of variables. Well, first and foremost, it's going to be a function of X, right? We talked about how the leading edge of the plate might have different heat transfer characteristics from the downstream region of the plate. So it's going to be a function of X. It's also going to be a function of the thermal conductivity of the fluid. For example, if you're flowing air over the plate versus water, you're going to have different effects, right? So it's the thermal conductivity of the fluid, as well as the fluid's density, viscosity, specific heat. Right? So all the properties of the fluid make a difference. What position we are makes a difference, as well as basically what the fluid's free stream velocity is, where U infinity, or you might call it V infinity, is basically what the free stream fluid velocity, what the free stream fluid velocity is. So we have h being a function of these 6 variables. It's almost the same set of 6 variables that we used for pipe flow, only instead of average velocity, we're using free stream velocity, and instead of diameter as a length scale, we're using x as a length scale. And, we could say, hey, does anyone want to do 10 to the 6th experiments to characterize this? Heck no, we don't want to use 10 to the 6th experiments. So we can do non-dimensionalization. Like we did in the previous lecture. And you can basically say Nusselt number sub x is equal to h sub x times x over k of our fluid, and this is some function of rho times u infinity times x over viscosity, and also of mu times Cp over the thermal conductivity of the fluid. And if you wanted to give special names to these things, well, this first one looks a heck of a lot like a Reynolds number. It's not a Reynolds number based on diameter like we've seen in the past, but instead a Reynolds number based on x. So we can basically say this Nusselt number is going to be a function of Reynolds number with x as the length scale for Reynolds number, and the Prandtl number, basically defined exactly as before, which turns out to be a function just of the fluid properties. We could follow a similar rationale for the average heat transfer or the average convection coefficient or heat transfer coefficient, which might be h sub L, which we would basically say is a function of length and all the same other parameters before. All of these same parameters before, only instead of depending on x, it depends on what the length of the whole plate is. And you can formulate Nusselt number in almost the same way. In this case, it's a Nusselt number sub L, and it's equal to h bar sub L times L over k of the fluid. And this is a function of rho times u infinity times L over mu, and mu times Cp over k of the fluid. And this is a function of Reynolds number with L as the length scale for Reynolds number and Prandtl number. One key thing I want to emphasize, these are not the same function. So whatever function would give me a local Nusselt number is not going to be the same function as what's going to give me an average Nusselt number. Even though the arguments look similar, and even if I subbed in L for x right here, this would not give me the same as what I had here, right? Basically, the local heat transfer coefficient isn't going to give me the same as what's averaged over the whole plate, because what's averaged over the whole plate basically incorporates a whole bunch of points that are not the point that I'm talking about right here. So they're not going to be the same function. They might be similar in a lot of forms. They have similar arguments. They might have a similar structure, but they're not going to give the same thing. So we need to choose which function we're using when we're investigating or trying to figure out whether whether we want to investigate local points on the plate or average quantities over the whole plate. So what do these functions depend on? What exactly do these functions look like? Are we going to build a chart like we did for the Nusselt numbers for pipe flow? Yes, but next time. So stay tuned for another lecture coming up where I basically talk through what these functions are going to look like. Spoiler alert, we're going to have different ones for laminar versus turbulent. We're going to have different ones for constant surface temperature versus constant surface heat flux. We're going to have different ones for local versus averaged. So stay tuned for all of that. All right, so thanks for watching. Hope you enjoyed and learned something from this lecture. Good luck with your study of heat transfer. Take care.